and please take away.
Do you see my screen, by the way?
Yes, we do.
Okay, then let me start. First of all, I'd like to thank the organizers for inviting me to give a talk at Swampland Seminar Series, and I'm sorry that I changed the title of the talk in the last minute, but today I want to talk about explicit constructions of KKLT ADS vector. Okay, and this talk is based on the work that I've done with my collaborators, Mehmet Demetis, Liam McAllister, and Jakob Moritz and Andres Rios-Tasca. So let me say a few words before I really begin. Our universe is not supersymmetric. This is one very simple observational fact. And even worse, our universe is expanding at an accelerating rate, or even better. One very discomforting thing to me is that we still haven't found a single fully explicit string compactification that is at least compatible with the simple observational fact. And to me, this is a very serious problem, and I really think we should fix it sooner than later. And in attempts to solve it, what you can do or try to do is to add some supersymmetry breaking to supersymmetric ADS4 vacuum to put your vacuum on the firmer footing. And this is the route that I'll take following the proposal made by KKLT. So let me give you one slide summary of the talk. One of the most important problems in string theory is to delineate the boundary between swampland and landscape. And today, what I'll claim is that now KKLT, like ADS vector, are part of the landscape. So let me give you a technical summary. We explicitly constructed KKLT like supersymmetric ADS4 vacuum, and we did so by finding flux vacuum with exponentially small W0 at weak string coupled. And we also did so by finding more than H11 minus independent terms in non-perturbative superpotential with constant far fields. And this is going to be very important. The leading terms in the non-perturbative superpotential arise from pure rigid prime toric devices. I'll explain what those jargons mean later. And in the class of vacuum, we have checked that we have ensured that G string is proportional to 1 over log of W0. And at the same time, the instantaneous supporting devices have volumes commensurate to log of W0. And due to the fact that we used the prime toric devices in a significant way to stabilize Kähler moduli, what we have ensured is a hierarchy between the device of instantaneous supporting device volume and the Klavier volume. And this will be very important later. And although W0 is not really a parameter, you can always think of it as the control parameter whenever some problem comes up in KKLT, like construction or a scenario or a proposal. You can go back to W0 and ask, what does everything do to the W0 or the value of W0? And the vacuum we constructed have exponential hierarchies. And the very seed of the exponential hierarchy was the exponentially small W0. And quite surprising thing to me is that in order to find exponentially small CC, we didn't have to find exponentially many vacuum. We had to find polynomially many vacuum. And even so, some of the vacuum we found have even smaller CC than that of our universe, although the sign is wrong. The reason why this was possible is because of the fact that the F-term potential in string compactification is purely determined by a set of integers, so that the exact cancellation between perturbative terms is not supernatural. And I think, in a way, these vacuum are solving a toy supersymmetric version of the CC problem. Of course, this is not the full CC problem, but at least it's giving me some hope that eventually string theory will tell us something about the grand scheme solution of the CC problem. The vacuum we constructed are systematically and heavily tested. What we did is to include string tree level alpha prime corrections to the Kähler potential by computing Göbel-Kumar alpha invariants up to very high degrees. And string loop corrections are suppressed because we have ensured that string coupling is really tiny. And each vacuum we constructed is characterized by a set of integers. So if you're curious about R vector, what you can do is to go to archive and download the file and check those vector by yourself. And the search is automated. This is why you don't have to have a huge insight, or you don't have to master a particular geometry to construct a vacuum. You just need to click a button, then you'll get a vacuum, just like that. Of course, search for de Sitter vacuum or quintessence is left for future, which is very exciting. So this is a rough plan of the talk. First, I'll review the KKLT proposal, and I'll tell you how we constructed supersymmetric ADS4 vacuum. And I think by the time I'm done talking about explicit construction, I'll have used up all the time, 45 minutes. But if I do a very good job in time, then I want to talk about de Sitter. And if I do not do that, please ask me some questions during the question session, because I want to tell you something about de Sitter, especially regarding the singular bulk problem. So let me start the review. What KKLT proposed back in 2003 was that you may be able to find de Sitter vacuums type 2B string theory compactified on Calabi-Yau threefold if you find the following ingredients and combine them successfully in a given Calabi-Yau compactification. And those ingredients are exponentially small W0 and non-positive superpotential to stabilize Kähler moduli, and the gas droids generating discretum of exponential hierarchies and anti-degree bands at the tip of the throat to break subsea. One very important point that I want to emphasize is that each of those modules is very well understood if you isolate them from each other. So if you just decouple them from everything, then you can understand them. But the problem has always been the case that combining those modules has been extremely difficult. And combining all of those four in one paper or in one work is, just too difficult. So what I'll do is to combine the first two to construct supersymmetric ADS4 vacuum. So how do we actually do that? So now the method to construct the KKLT ADS4 vacuum is completely systematic and algorithmic. So I want to tell you what the algorithm is. What we do first is to pick a pair of 4D reflexive polytopes from the Kreutzer-Skaka database. Then what you do is to construct the Calabi-Yau, a mirror pair of Calabi-Yau manifolds by triangulating those polytopes. Let's say we want to find the KKLT vacuum in Calabi-Yau X. And what you should do is to construct an orientifold of X and find its aptherium left to control some non-productive effects. Then what we do is to find more than or equal to H11 rigid divisors and compute non-productive superpotential terms. Then now we finally want to stabilize complex structure moduli and find some flux vacuum with small W0. To do that, what we need to do is to understand complex structure moduli of X. To do that, we use mirror symmetry and compute Kuperkumov alpha invariance of mirror Calabi-Yau of X, and then find flux vacuum with exponentially small W0. Then, given the exponentially small W0 and the non-productive superpotential, you can stabilize Kähler moduli, but this is not the end. What we need to do is to compute Kuperkumov alpha invariance of the original Calabi-Yau X in order to check the alpha prime control or alpha prime expansion. And this is the whole algorithm. And what you need to do whenever you find some problem at each step is just to go back and find a different reflexive polytope. And you do that over and over and over again. Of course, this is a long list, and it is practically impossible to go through each one of them. So I'll just pick four, most important steps. So I'll first tell you about how you can find exponentially small W0, and then I'll tell you how you can find the non-productive superpotential terms, and then I'll tell you how you can stabilize Kähler moduli, and then I'll tell you about alpha prime corrections.
Manki, one question. So
yes,
is it clear that you are controlling all the important alpha prime corrections just by checking these GV invariants? Like, what about the superpotential corrections and so on?
That's a very good question. And yes, let me just give you a brief comment. So obviously, we are not able to compute all the alpha prime corrections, but given that we have ensured that string coupling is really tiny, all the string loop corrections are suppressed, which means that you just need to compute the string tree level alpha prime corrections. That we can compute using mirror symmetry. So string tree level alpha prime corrections we can just compute to any order that you want to. But there are some other corrections that we do not want to. We do not know how to compute, but we really want to compute. But at the moment, we have no tools to compute them.
Are your radii that you're stabilizing much bigger than string scale?
Curve volume. Okay, that's also a very good question. After stabilizing Kähler moduli, Einstein frame divisor volume are big, and string coupling is also big, which implies that Einstein frame divisor volume is order 1, and some curve volume string frame divisor volume is order 1, and string frame curve volumes are quite small. So that is quite worrisome. But what we found is that most of the small curves are actually flop curves, and then we know exactly how to control those flop curves. You can just find the.
No, I'm not worried about curves. I'm not worried about curves. The whole action is not under control. The Einstein action is not under control. If your curvatures are order string scale, then you have to go not just r squared, r cubed, r to the n. What are those? How are you doing those? The whole Calabi-Yau goes to smithereens.
Given that we have ensured that the Einstein frame volumes are quite large, I don't think the curvature should be string scale.
Well, if you work in the string frame, if your curvatures are order of string frame curvatures, the corrections of string theory involves alpha prime corrections.
Yes.
And therefore, there will be all of order, relevant order. You cannot ignore those.
Yes. Oh,
so
we did not ignore them. And then we computed what we can compute. And for the Calabi-Yau volume, at least in string frame, is quite big. At least the string frame Calabi-Yau volume was at least 10 to the 3. So it's not small.
So this volume, I thought that was my question. The sizes of the curves that you're choosing in string frame, are they big in string frame or not? That was my question.
The small curves in string frame, there are some small curves in string frame volume, but those are flop curves.
Well, as long as you have any region where you have curvatures over the string scale, then you have the question comes up that the one I'm talking about. And from those regions, you get corrections to the Einstein action and all that. How do you deal with those?
So the corrections from small string frame curve volumes, especially if they are, it doesn't matter whether or not they are flop curves or not. What you can do is to use mirror symmetry to compute the corrections to the Kähler potential or the Einstein action.
No. I'm in a much more worse situation than you're thinking. I'm saying the whole action breaks down. You're assuming that we can trust the action after that. The whole string, whenever you're dealing with stringy corrections, you want to make sure that you're in scale much bigger than string scale, everything. Otherwise, the string theory breaks down. The whole thing breaks down, even if G string is very small.
Yes, the whole thing breaks down.
This is a usual story. I'm not saying anything amazing. This is a well-known situation, right? Your string theory perturbation breaks down.
Yes.
Then how are you talking about string perturbation? I don't get it.
Well, what I'm saying is that let's say we go to N2 SUSY and then we write down pre-potential. We can totally do that. And then you know that
pre-potential assumes a given geometry. I'm saying you don't know what's your geometry. It's not Calabi-Yau. What are you doing?
Yes, I know. But what you know is that your effective action breaks down if the instanton expansion is not under control, right? If the instanton expansion is under control, then you know that your EFT or expansion is well behaving. Nothing is going crazy.
No, I'm not talking about instanton. I'm talking about string alpha prime correction. It's not instanton.
Yes.
I'm talking about alpha prime corrections, which is not instanton. I'm talking about much more basic corrections. But maybe I should let you go on because I don't understand. I don't want to derail your talk. Go ahead.
But instanton corrections are part of the alpha prime corrections. And okay, but anyhow, let me move on. So you need to find W0, which is exponentially small. And from Denef and Douglas and Douglas, what you learn is that if you study complex structure moduli space statistically, then you realize that exponentially small W0 should occur, although the frequency that exponentially small W0 occurs is exponentially small. This is why it's been really challenging to find exponentially small W0 by brute force searches. But by now, we have a mechanism to find flux vacuum with exponentially small W0. And this mechanism was applied to many explicit examples, and this mechanism was extended to many other singularities, even including conical singularities. So if you want to find similar W0 with some druids, KS druids attached to the Calabi-Yau, you can totally do that. And this mechanism can be efficiently implemented to find exponentially small W0 at small h1, but still finding flux vacuum at large h1 is technically challenging, and we're not going to touch that issue today. So let us try to understand the flux vacuum with exponentially small W0 at large complex structure and weak string coupling. At the large complex structure, what you can do is to write down the flux potential in terms of derivative and instanton terms. And what I really want to emphasize is that flux potential is purely classical. So whenever I'm saying derivative and instanton-like terms, it just refers to the type 2A or the mirror structure, because we're using the mirror variables to write down the flux potential. Some terms look like derivative terms and some terms look like instanton-like terms, but it's purely classical. What we have shown is that you can find fluxes F and H such that there is a derivative moduli space, which is parameterized by the axiodilaton, in which the derivative terms in the flux potential exactly cancel. And then at this point, you have massless axiodilaton, but to stabilize axiodilaton, what you do is to include the instanton-like terms in the superpotential. And a very important point is that all those coefficients exponents in the instanton-like superpotentials are computed explicitly using Goebbels-Kummer alpha invariance, fluxes, and intersection numbers of the mirror Calabi-Yau. And assuming that, or provided that you have engineered or you have found a successful racetrack, you can obtain exponentially small W0 at the after minimum. And as a result of that, string coupling is also quite tiny, and mass of axiodilaton is commensurate to the mass of Kähler moduli. But this is not a bug, this is a feature, we can totally work with it. Let me go into an explicit example. We constructed a Calabi-Yau X with 113 Kähler moduli and 5 complex structure moduli, which is defined as a hyperplane in a toric fourfold given by a reflexive polygon. And we also constructed an orentfold in such that there is no geometric moduli projected out, and the degree range table of the orentfold was 60. And we chose some fluxes F and H by using a 56 flux quanta. And then if you write down the flux superpotential, what you realize is that indeed there is a derivative moduli space, and the leading instanton terms in the flux superpotential are rising from the mirror curves with GV invariance -2 and 252. And then you can write down the instanton terms like the flux superpotential, which is given by the formula that I wrote down. And if you minimize the flux superpotential, what you get is W0, which is exponentially small. And the string coupling is also quite tiny.
Sorry, I'm a bit confused. Do you have D3 branes in your story or not?
We have D3 branes in our story.
But if you have D3 branes in your story, there are new rigid superpotentials terms generated by D3 Euclidean D3 branes, which pass through those, as we pointed out in my paper with Timo and Aaron. Where have you included those?
What do you mean by, could you say that again? You said—
in my paper with Timo and Aaron, we showed that if you have extra D3 brane, the original literature where people studied the superpotentials in F theory ignored Euclidean D3 branes, which pass through the D3 brane probes.
Mm-hmm.
And some things which were not rigid become rigidified when you have D3 brane probes.
Yes.
So where have you included those, and how do they impact you?
That's a very good point. So by rigidified, you mean some Euclidean D3 brane instantones that were not rigid but rigidified so that it introduces some new terms in the non-protected superpotential. Is that what you're meaning?
Yes, there will be new superpotential terms which involve happening to the D3 brains. Where are those?
Yes.
And regardless of those, even if they weren't those, how have you stabilized the D3 brains?
Okay, there are a few comments that I want to make. What we did in order to stabilize Kähler moduli was to pick prime toric devices or prime toric devices such that so basically in each clavier, in every clavier threefold, you have H11 plus 4 prime toric devices. And what we did was to choose H11 prime toric devices. And then those H11 prime toric devices have the smallest volume among all the devices that you can find in the clavier. And given the fact that we used the leading terms in the non-protected superpotentials are generated by those H11 prime toric devices, and they are rigid and they are pure, even if there are some other devices that are rigidified by the ED3 instanton, sweeping through some D3 brain, there are some limiting compared to the prime toric devices that we considered explicitly. But if you really want to make a very precise computation, then you need to include those high order corrections in the non-protected superpotential, but there are some limiting.
No, my worry is that if you don't take those into account, how do you know where the D3 brain are stabilized or what? How are you stabilizing your D3 brain positions?
You can stabilize D3 brain positions by having some non-protected superpotential. You're correct, and then we are assuming that the D3 brain moduli are stabilized at F minimum. And of course, at this point, you cannot explicitly show or explicitly compute where those D3 brains are, because we do not have the clavier metric, but it's purely technical. And then by many papers, it was shown.
I disagree that it's purely technical. In original KKLT type arguments, they were saying that D3 brain moduli is compact and it will find the minimum. And that was a mistake, because just the same reasoning will tell you that the D7 brain moduli in FDA are compact, and therefore there will be no infinite distance in the moduli space of elliptic K3, which is false. That reason.
No, I'm not arguing based on the some argument like the D3 brain moduli space is compact, therefore it is inducing no problem. What I'm saying is that if you consider some D3 brains on some in some background with some non-protected superpotential, what you realize is that there is an interaction between D3 brain moduli and the non-protected superpotential terms, which was initially studied by Kähler. So what you realize is that you can move your D3 brain around some instanton or Euclidean D3 brain instanton or the Gaugena condensation. And what you realize that there is some phase factor, which implies that the Wolff-Appian of the instanton superpotential terms is actually a section of some section of a line bundle that knows about the D3 brain position. And then using that, you can stabilize the D3 brain moduli. There is no problem. I'm not arguing based on the compactness or whatever of the D3 brain moduli space.
How do you know it's stabilized when you haven't even included the terms I'm talking about? I'm talking about the extra superpotential terms that you have not even included. How do you know it's stabilized? I don't even
No, they are included.
They're not the ones I'm telling you. How did you include those? Nobody has studied the one I'm talking about.
Perhaps I can clarify. I think there's a few. These instantons here are not the D3 instantons. They are like the mirror to the wall-sheet instantons in 2A. So we haven't reached the D3 story yet. I think when we reach the D3 story, then there are questions like, how do you know that the instantons you included are the only relevant contributions to the superpotential? Because there are also other ones, and also even instantons that are rigid still can have D3.
Like which kind of instantons are you referring to?
Maybe we'll talk about that when we come to the D3. But perhaps I have a question already at this stage. Can I ask that maybe? Or,
sure, please.
In what sense is this W0? In the sense that, I mean, as I understood W0 to be as an effective constant superpotential in the sense of an effective theory where you've integrated out all the massive complex structure moduli.
Yes.
But here it seems to me that you just have basically doing racetrack. So racetrack was what people were doing before KKLT. That's a step back from KKLT.
Well, yeah, that's a very good point.
You have essentially W0 is 0, and then you have racetrack. I mean, yeah.
Yes. That's a very good point.
What is new here?
So, okay. Due to the fact that one complex structure modulus or a linear combination of complex structure moduli plus exodilatum modulus is very light, we cannot just say that this is a pure constant. If some Kähler moduli stabilization is heavily affected by the complex structure moduli stabilization or vice versa. So suppose that one of the non-positive superpotential terms heavily depend on complex structure moduli or the exodilatum. Then we cannot just say that W naught is a constant because the mass of
depend on it. I mean, the F terms, you have the whole superpotential in the F term. So it's
yes.
So they don't have to depend on it. It's a well-known, I mean, even in KKLT, people were discussing whether it's consistent to integrate out the complex structure moduli and treat this as a constant and then integrate out this two-step process. And even in KKLT, it was kind of people debating it. Now, in this case, it seems to me that it's just in racetrack. I mean, racetrack, we could do also in heterotic. We can do racetrack anywhere. I mean,
yes, you can do racetrack, but the point that I want to convey is that we're not integrating out the light complex structure moduli. When we're actually stabilizing the Kähler moduli,
what is W0?
You should also...
What is W0 then if you're not integrating it out?
Okay, so if you neglect everything about Kähler moduli, then you can say about W. But what you really need to do, in fact, when you're stabilizing Kähler moduli is to include all the terms in the non-positive superpotential and including the racetrack terms and then explicitly stabilize Kähler moduli and complex structure moduli at the same time. But what I want to really emphasize is that due to the fact that due to the technique that we're going to use to ensure that the one-Hoffian of the non-positive superpotential terms do not depend on the complex structure moduli nor the exodilatum, actually it turns out that you can just treat the W naught and the non-positive superpotential terms are separate or don't talk to each other. And this is due to, and one outcome or one result that you can see by explicitly stabilizing Kähler moduli and complex structure moduli at the same time is that you get the W naught, you ignore all the Kähler moduli stabilization, and you get the value of W naught and the value of G string. And then what you do at the same time is to stabilize Kähler moduli and the exodilatum and complex structure moduli.
How is this different to just taking, like, say, I take a heterotic and then I take some instantons that depend on some moduli, some instantons depend on other moduli. I say, oh, I take this sector of instantons, I call this my W naught, I minimize that, and then I balance the other terms against that sector. Well, you just have two sectors of instantons here that for some reason you're distinguishing one from the other. And then fixing one of them and then balancing the other sector against this sector.
I'm not fixing one of them and then balancing one other from the other. It's just the matter of convenience. So what I should really do is to just stabilize complex structure moduli and the Kähler moduli at the same time. But the reason why this is a convenient thing to talk about is due to the fact that when you include the Kähler moduli stabilization, then the value of the W naught or W naught is basically like let's say I just conveniently
But I just said you can call anything W naught. Why don't you call the Kähler moduli W naught? You can call that W naught. I mean, you just have two sectors.
Right, you're correct. But what I'm just saying is that I just conveniently define the VAV of the everything that comes from the flux superpotential W naught. But it doesn't mean that the W naught or the VAV of the flux superpotential is meant to be fixed even when I'm stabilizing Kähler moduli. It's just a matter of jargon or, terminology.
I mean, it seems the precise statement is W naught is exactly 0, and then you just have racetrack. This seems to me what the statement is. No, and then afterwards you can say, oh, we have racetrack and we have two sectors in a racetrack, and we believe that even though there's no mass hierarchy, they decouple from each other. Maybe you believe that or don't. I don't know if that's true or not. I don't know. It seems to be very suspicious.
It's not a matter of belief. We have computed it, right?
Like you have computed the 100 exponentials. You computed the superpotential of 100 exponentials.
Oh yeah, we can do that. We can totally
minimize this 100 exponentials.
Maybe we can let Manki continue with his talk, and then we can keep talking about this when he's finished presenting the results.
Okay, that's fine, but it's obviously a very central issue. So
yes. But let me just tell you, you can just go up to the higher orders in instanton like superpotential and then just do the whole racetrack if you want to. You can totally do that, but you can show that actually some leading instantons due to the high order GV invariance are really tiny compared to the leading terms. And that's why we ensure, we think those vacuum are legit. And it's just not that we're believing it because we have shown.
It's fine. We don't need to discuss it. My point was just there is no W naught if you really strictly speak about it. It's essentially a race.
Oh
yeah,
okay.
That's the only thing I wanted to say. Yeah. Okay. Thank you.
Sure, but this is a matter of terminology, and Of course, like if you want to say that, then that's totally fine. I'm happy with that. But the only reason I'm talking about W naught is because it is more simple to describe what is going on. But you're correct, it's purely racetrack in the end. Okay, now let us talk about computing the W naught productive. So, okay, there is some, some people may not like the name W naught or whatever, but let me just say we have arranged the racetrack for the complex structure moduli stabilization, and we want to complete the full superpotential, or not full superpotential, but by including terms, non-productive superpotential terms. What you need to do in order to ensure that some non-productive superpotential terms are not vanishing, or there are some non-productive superpotential terms, is to ensure that the divisor in question is rigid. By doing so, what you can show is that the one-Lagrangian of some particular terms are not zero at generic points in the moduli space. Basically, what it means is that some divisors have no Wilson-line moduli, no deformation moduli. This is simple. But still, computing the one-Lagrangian is very difficult. But at least what you can do is to show that the middle cohomology group of the epithelium left divisor is vanishing, to make sure that the one-Lagrangian is constant. This was closely, in very detail, studied by Witten in '96. So let us go back to our example. We want to find the Clavier with superpotential W0 plus non-productive terms in the superpotential. And what I require is that there are more than or equal to H11 prime toric devices that are rigid and pure. The reason why we require that is first because of the fact that complex structure moduli is very light, and we don't want the complex structure moduli stabilization is spoiled by some Kähler moduli stabilization. Basically, we want to do a very clean, nice racetrack. And let me assure you, this racetrack is not something that we made up. We computed each term in string theory. And the reason why we take the prime toric devices instead of like some wacky devices or big devices in the Clavier is because we wanted to engineer some hierarchy between instant and supporting divisor volume and the Clavier volume. And this fact will be quite important later. So let us go back to the explicit example. We took the Clavier with W0 as small as 10 to the minus 62, and the flux quanta is 56. In this Clavier, there are 117 prime toric devices, and one of the prime toric divisor hosts in a 7-plane, and this prime toric divisor is big in a Kodaira sense, and this prime toric divisor has 2 deformation moduli. There are 25 rigid devices hosting non-hexable clusters with no moduli whatsoever, and those non-hexable clusters have SOA gauge groups. There are 89 rigid devices read by 83 brains, and those devices are also pure. And there are a few more rigid devices but they're not pure. So let me just skip them. And what we do is to place the 7 brains on top of the 7 planes to cancel the 7 brain tadpole locally. But this does not ensure that the 7 brain moduli are stabilized yet. I'll talk about that later. And let me emphasize, the SOA stack on the big divisor will not play a significant role in stabilizing Kähler moduli. Then you can write down the superpotential, and the resulting superpotential is given as a sum of W0 plus some non-productive terms in the superpotential. And let me emphasize again, those one-Lagrangians are pure constants, and as Aaron pointed out, W0 is really a value. It's actually depending on some light complex structure moduli, but you can just deal with it. Okay, now we have found the superpotential. Now let us talk about stabilizing Kähler moduli. As I told you, we have found superpotential W0 plus non-productive terms in the non-productive superpotential, and we want to solve the F-term equation numerically. A technical remark that I want to make is that there are exponentially many Kähler cones in the extended Kähler cone at large H11, and after minimum for the ADS vacuum is exponentially rare. So this is why we had to build a very efficient algorithm to find a KKLT like after minimum in the vastly big extended Kähler. So to give you a sense, let me show you a 2D cross-section of the extended Kähler. It's not actually the extended Kähler, it's rather the secondary fan, but they are roughly the same thing. And what you can see is that each dot or each color or each island in the picture is describing a different distinct Kähler. And you can see, and this picture was made for Calabi-Yau with H11491. And you can see that there are exponentially many Kähler cones in the Calabi-Yau. And what you will realize is that only a handful of Kähler cones have after minima. So the after minima are exponentially rare. So in a way, the KKLT ADS minima are highly non-generic. They are not, and they cannot be represented by generic points in the moduli space. And after stabilizing Kähler moduli G-string and W0 are at less than 1% level, we check them explicitly. And you might be bothered by one fact, which is that I did not tell you anything about the numerical value of the Lorentzian of the non-positive superpotential terms, which we cannot compute at the current point. But it turned out that the numerical value of the Lorentzian doesn't heavily affect the Kähler moduli stabilization, provided that the value of W0 is very small. So, and then we actually scanned through the possible values of the Lorentzian. We obviously didn't find a huge deviation from the original after minimum. But anyhow, you can do that. So let's go back to the explicit Calabi-Yau. We found W0 as small as 10 to the minus 62 by using 56 flux quanta. And we found living terms in the non-positive superpotential terms, and those arise from pure rigid prime torque devices. At the KKLT after minimum, we have computed that the ED3 instantaneous supporting prime torque devices have Einstein frame volumes 22. And prime torque devices that support SO8 non-hexable clusters have Einstein frame volumes 132, roughly 6 times that of the ED3 instantaneous supporting devices. Rest of the prime torque devices are huge, as you can see. And this is a seed for some hierarchy between the instantaneous supporting device volume and the Calabi-Yau volume. So let's take a look at how do those Calabi-Yau look like. So basically, they look like a long baguette with some holes, with some ED3s. And the very point that I want to emphasize is that at the KKLT, like after minima, Calabi-Yaus are highly asymmetric. Many of the devices are super tiny compared to the Calabi-Yau, and there are a very handful of devices that are really big. So let us talk about the open string moduli stabilization and alpha prime corrections, which is a hot topic today. There are 4 D3 brane moduli and this 8 D7 brane moduli I didn't explicitly stabilize yet. Let's first talk about D3 brane. What was known by many works or many papers is that D3 brane moduli actually show up in the Lorentzian of the non-positive superpotential terms due to the Kähler prefactors. And then what was shown is that you can place the D3 brane positions or D3 brane moduli at after minimum. Although we did not do it explicitly, in many papers it was shown that you can place D3 brane at the after minima while not encountering any runaway direction. It's not because we're dealing with some compact moduli space, it's because the D3 brane moduli dependence shows up in the Lorentzian of the non-positive superpotential terms. And what I told you is that the 7 brane tap holes are cancelled locally, and we did so by placing the 7 branes. Yes?
So where is the D3 brane minimum that you place it? How do you work it out?
Okay, at this point, we are not able to compute the D3-brane minima or find D3-brane minima explicitly, because in order to do that, you need some Calabi-Yau metric to compute the distance between the D3-brane and some instance supporting devices.
So when you say you place them at the minimum, you mean you let them go wherever they naturally want to go, but you don't know where they go.
Right.
And how do you know then that they don't make some of the instantons that you use vanish? How do you know that they don't make some of the instanton terms that you use vanish?
If you place a D3-brane on top of some ED3-brane, then they vanish. That is a real possibility, but that's kind of a runaway direction. And what was shown is that, you can just place.
It's not runaway. Why would it be runaway? It's just the minimum. The minimum is on top of the instanton.
No, of course, like I'm exaggerating by a bit. Like, suppose that you place D3-brane, a single D3-brane in every each one of the instanton supporting devices, then you don't have any non-protective superpotential.
No, but I mean, you said you found these H1 different devices and then you use them to fix the moduli. How do you know that some of them don't disappear because D3-branes flow on top of them? Especially given that they are the leading contributions to the potential. So if they're the leading contributions to the potential, then D3-branes would naturally want to flow on top of them, I would guess.
D3-branes do not. Okay, so if you move D3-branes too close to the instanton devices, then D3-branes are repelled. And then if you move D3-branes away, too much away from the instanton supporting devices, then they're attracted to the devices. And this kind of behavior was studied explicitly in some local Calabi-Yaus. But of course, I agree that
what is changing their behavior? What are some heavy string modes or what? Why would they be attracted and then become repelled? I thought that the potential just vanishes if they go on top of it. That sounds to me like a minimum. No? Maybe I missed that.
It's a run. If you do that, then some of the divisor volume do not show up in the leading instanton superpotential. So some of the directions will be a runaway direction.
But maybe it's not runaway, it's just that leading term cancels and then you get the subleading that makes the complex structure
that
and
could also
the
be
Kähler
a
moduli.
Possibility. Yeah, that is so also a possibility.
Subleading terms that are mixing both sectors that you usually neglect, maybe they become important in that case, no?
That would be quite surprising though, because of the following fact. So basically, to make that happen, you need to have some, like some big devices combined with ED3 and all that, but they have many moduli, which is kind of saying that those are not easily showing up in the non-protective superpotential terms. So if you go higher and higher in divisor degree or like divisor class, you usually find that there are many moduli associated with the divisor. So if you do not, rigidify those divisors by doing something special, then they don't show up in the superpotential.
Sorry, stupid question. Can you not avoid the D3s by adjusting the flux?
Yes, we can do that. So we can totally find flux factor by using a. Oh yeah, that's a very good comment, Arthur. Thank you. We can totally find a flux factor with no residual D3-brane moduli, but in our example, we did kind of some different thing because we wanted to make W0 as small as possible. But if you're being modest about the value of W0, we can totally do it, and there is no residual D3-brane. So I don't think this is a very serious issue. Of course,
the point? Like it's more difficult to stabilize the D3 with fluxes this way if you want to keep W0 small at the same time.
No, it's just okay. So we do not know how to predict the correlation between the value of W0 and the D3-brane charges that we're using by the flux quanta, but typically, like I think maybe someone in the audience may know, but I don't think we have seen some clear pattern between the D3-brane charge. Of course, if you use more D3-brane charge, then there is more possibility to do the cancellation or more fine tuning. So
I'm
usually,
perhaps confused. I thought your point here is to be explicit, but you're now resorting to generic statements and this and that. So it's not the exact explicit example because you're controlling some of the questions, you're not controlling other questions. Do you have any examples where you can control everything with the small W naught at the end, including whatever else that comes in? That's the kind of question I think would be worthwhile doing rather than trying to assume, this genericity will be this and that.
Yeah, we can find and we can give it to you a flux vacuum with W naught, and we can do so by using all the flux quantum. That's not a problem. We can do that.
With the small W naught, that's the question.
Oh yes, small W naught is okay, but we cannot just get to extremely small W naught like 10 to the minus 16.
So those are, I would say that it would be much more interesting probably to focus on examples where I have no D3 vein, as Arthur suggested, because then you will get rid of a whole host of problems like the ones we are talking about. And then focus on the remaining issues that people are asking, like, what about the alpha prime corrections? What about this and that? And then within that class, what is the smallest you're getting W naught? Those are, I think, would be a more promising avenue to go.
Well, yeah, that's a good point. Maybe like a flux factor without any mobile D3 vein would be more clean. Okay, so yeah, I cannot recall the statistics of flux factor with no mobile D3 vein on top of my head, but I can go back and check. But there are certainly many. Okay, so, and we cancel the 7 brane tadpole locally by placing the 7 branes on top of our 7 planes. And the question you should ask is whether or not the 7 brane moduli is stabilized. There are some genericity arguments saying that yes, the 7 brane moduli might be stabilized, but as we all know, this is not fully convincing. So what we're doing in addition to it is to compute the D7 brane superpotential explicitly to show or check that whether or not the D7 brane moduli is stabilized. This is an ongoing work, so stay tuned for the result. I think we'll be able to learn how the D7 brane moduli is stabilized quite soon. Okay, now we have stabilized some moduli, all the moduli. Let's talk about alpha prime corrections. So Einstein framed divisor volumes and one reduced string scales as log of W naught. Although it is kind of good because you have ensured that you can use supergravity because Einstein framed divisor volumes are big and one reduced string is large. But this could be a double-edged sword because string frame divisor volumes are order 1, although string frame Clavier volumes are big, just because of the fact that H11 of prime toric devices have order 1 string frame volumes and the rest of the prime toric devices have really big string frame volume. And some string frame curve volumes end up very small. So this is indeed scary. So what we did was to compute alpha prime corrections that we can do by using Gopa-Kumov alpha invariance and the mirror symmetry, and those kinds of alpha prime corrections that are the ones that you can compute, assuming that string loop corrections are suppressed, and they are suppressed because string coupling is small. And the rest of the corrections are just coming from the string tree level alpha prime corrections to the Kähler potential. And we computed Gopa-Kumov alpha invariance to enumerate the alpha prime corrections. But what you can still ask is whether or not those the instanton expansion is under control. Do you have any question, Aaron? Or
yeah, I don't understand they're like non-perturbative at alpha prime.
Yes.
So what happens to all the perturbative alpha prime corrections? Why are they not important?
Okay, that's a very good question. The way that we're doing is as follows. So the leading order, we're starting from N2 compactification and then break the SUSY by half, right?
Yeah, but this is an N equals 2. This is a string scale cycle with I mean, the manifold's not even locally Calabi-Yau. It's like the instantons back react in a way that it's not even locally. These instanton cycles are string size, and there's no remnant of the n equals 2 structure. I mean, it's we don't even know what the manifold is locally because you have to back react the energy density of the instanton.
That's true, but that doesn't mean that you cannot do anything. As long as the perturbation that you're making from the N2 or the Calabi-Yau is manageable, you can still use the structure of N2 structure or N2 SUSY or the.
So you say that I can take an n equals 3 compactified on whatever manifold I want at string curvature and have that under control. I mean, what is special about this compactification that allows you to have string curvature and that we cannot have in any other kind of manifold compactification?
It's not string curvature. It's
the cycles are string scale, no? I thought.
Oh yeah, but okay. So let's take some simple example, N2 compactification, and then you have some Calabi-Yau with some curves, which are flock curves. You can totally shrink those flock curves. Nothing crazy happens. Of course, there are some curves that are not flock curves.
I don't understand how you can shrink them to.
It's just basically a conifold transition, or like you can totally go to a conifold.
We don't have a supergravity effective theory that's valid at arbitrarily small volume, arbitrarily high curvature in small volumes. I mean, conifold translation is something you do in n equal. It's pure n equals 2, so that's why you have the control over it, and then you just write some effective theory with d term, the things it's not like we can write the at zero. We know the theory and the topology changes and stuff like that. So we can have some effective.
But I'm really confused. Like I think you can totally write down effective supergravity or effective gauge theory or Cyber-Witten theory or whatever, even if you're approaching some conifold singularities. That's totally legit. I don't know what the problem is.
If you're n equals 2, you might have a chance. Even then, there are issues. But this is certainly not. This is very far from pure n equals 2.
I didn't say that because the effect of SUSY breaking is enumerated by the size of W0. Basically, if you have large W0, then you break SUSY in a very ugly way. But if you basically the size of the superpotential is telling you how awful the SUSY breaking is, right? How far you're from N2. But W0 is, or the value of the superpotential is really tiny.
The W0 is a global object. The curvature is a local object.
Yes.
How can that be? How can W0 determine the local curvature?
What I'm telling you is that the local curvature matters, obviously, but the ones that matter are not the flock curves. For the flock curves, you can just do Cyber-Witten geometry and then perturb it using some supersymmetry breaking effect. When you shrink some curves that are flock curves, what you basically get is Cyber-Witten theory. And then you can totally perturb Cyber-Witten theory to go to n equals 1 supersymmetry.
Sorry, but you have O-planes everywhere. I don't understand. I mean, I'm here on Aaron's side. I mean, you have O-planes.
It's not just the O-planes. The instantons themselves back react. They have energy densities associated to them, and they deform the manifold away from Calabi-Yau. So instantons.
Yes.
So locally, you have a string scale geometry that is not Calabi-Yau. It's got nothing to do with Calabi-Yau. We don't even know what it is. It doesn't even have SU3 structure. There's O-planes, like I said.
Sure.
There's no remnant of the n equals 2 locally.
No. I strongly disagree with you. There are 2 points I want to make. Yes, there are also O-planes everywhere, but we canceled the O-planes or replaced all the D7 branes or D3 branes on top of O-planes. So those O-planes are scrimmed. And the other point that I want to emphasize is that...
Sorry. You can cancel the O-plane tadpole, but on the O-plane, there are operators, which are not n equals 2. And so
yes.
And your small cycles are close to the O-planes. And I'm worried about all kinds of operators that are arising in that context, which I don't see how you control them. On the O-planes, you have operators which are simply not there in the Calabi-Yau.
Yes.
And they're not cancelled by the TED. That has nothing to do with the tadpole. It's just the fact that you have different alpha prime corrections at the O-plane.
But aren't those alpha prime corrections usually coming with the G string times they were suppressed by G string times some tadpole divided by the volume, string frame volume, compared to the Lytton terms? And then what we checked is that, so that is correct, your comment is correct, but usually those, you can, of course, this is an EFT argument. We do not know how to compute them explicitly, but those corrections you of the O7 plane or O3 plane on some O7 plane or d3 plane charge divided by string frame volume. That's true. That's why we're worried if string frame. Are you still there? Yeah, but we have enumerated those parameters. Of course, it's not a proof that all the corrections, all the new alpha prime corrections are small, but at least can enumerate whether or not those alpha prime. Did you hear me?
Okay, so I think we lost
Hello.
Manki. Manki, you're back.
Yeah.
Sorry. Unfortunately, the connection was not good for a while. Could you repeat the last part of your answer? Because
we
didn't quite hear it.
Yeah. So what Arthur pointed out is correct. There are new operators included when you have some O planes and some devices intersecting O planes and all that. But at least what you can do. This is due to the fact that we're not really strong and we do not understand string theory much, but at least what you can do is to enumerate the suppression factors of the corrections that appear. And the suppression factors that you have for those new operators is the following form: G string times some D3 range tadpole or the number n or 3 planes or whatever divided by string frame volume. That's why we're really worried if the string frame volume is small, which means that this suppression factor is really large. And so what we did was this suppression factor for Was I disconnected again?
Sorry, Manki. Yes, you were disconnected again. Could you? Yes, very sorry about that. Could you just switch off your camera to see if that helps?
Yes, I'll stop using my camera. And could you hear me again? Could you hear me now?
Yes, we can. We can hear you.
Okay. So what I was telling you is that, of course, those new alpha prime corrections introduced by breaking SUSY from N2 to N1 are something that we cannot compute at the moment. But at least the least thing that you can do is to enumerate the suppression factor. And those suppression factor is given by G string times the number of D3 range charges induced from O planes divided by string frame volume. And that is why we're supposed to be worried about the small string frame volume or large string curvature. And what we did check explicitly was that suppression factor that is always coming along with the new operators introduced by N1 breaking is really suppressed. Typically, they were at least smaller than 10 to the minus 2 and 10 to the minus 3. That's why we're kind of, we think that those corrections to the new operators are small. Obviously, we do not know how to compute them. So if anyone could compute them, please do so. We'll be eager to know them. But at this point, the best thing we can do is to enumerate the suppression factor and then see what goes on. Any other question? Okay, then let me move on. We should still ask whether or not the instanton expansion is under control. Because you may still think that the reason why we get small corrections from the instantons is because we didn't go far enough in the instanton degrees. And after some point, you may think that the instanton may start to blow up. So to really show that that is not the case, we had to go really deep in the Morricone. Let me just quickly skip some technical details. But what we did was to define some control factor psi, which is basically Gopak-Kumov up invariance times 2e to the minus 2 pi string frame curve volume. And then we went really deep in the Morricone, and then we found 1728 rays of non-vanishing Gopak-Kumov up invariance, and those rays span 101-dimensional subcone of the full Morricone. And then, as you can see, they're decaying exponentially, very fast. So this is a very strong indication that the alpha prime corrections, at least coming from the Walsh instant terms, are under control. Now let's take a break. We constructed, I claim, we constructed explicit KKLT-like supersymmetric ADS4 vector, and each solution is characterized by a set of integers. The vector we constructed, I think, are systematically tested. And to find exponentially small cosmological constant, we had to find polynomially many vector. From that, you can kind of learn that string theory oftentimes defies naive EFT expectation, and the search is automated due to the SWI tools that Mehmet and Andres developed. And if I have some time, I want to talk about distant lifting, but if I do not, please ask me some questions about distant lifting. I want to talk about the singular bulk problem, which is a very important serious issue in the KKLT construction, if the time permits.